Assalamu alaikum. This is Naima Khan. Today I am going to take you beyond the radar and missiles to the chemistry that powers the entire world of air defense. While we usually associate these systems with engineering or physics, their real power comes from chemistry. The invisible force that drives propulsion, destruction, sensing, and protection. Let's explore how molecules and materials come together to defend the skies. Air defense systems are amazing wonders of modern engineering, but their capabilities fundamentally rely on sophisticated chemistry. From the powerful propulsion that launches missiles at incredible speed to the precise guidance and enabled by the advanced sensors and the destructive force of their warheads, every aspect involves a deep understanding of chemical principles. First, let's talk about what gets a missile off the ground: the propulsion. Most air defense missiles rely on solid rocket propellants. These typically contain powdered aluminum or magnesium as fuel and ammonium perchlorate as the oxidizer. When ignited, ammonium perchlorate breaks down and releases oxygen, causing the metal powder to burn at incredible speed and temperature. Here is a reaction where the ammonium perchlorate is break down into nitrogen, chlorine, oxygen, and water. To hold all this together, we use a rubbery compound called HTPB, which also helps burn consistency. Additives like boron make the reaction even more energetic, and iron oxide acts as catalyst to control the burn rate. Some missiles use liquid fuels, often dangerous but highly reactive. These hypergolic propellants ignite the moment the fuel and oxidizer touch, offering extreme precision and rapid launch. The examples include toxic hydrogen derivatives like UDMH paired with nitrogen tetroxide. Their precision and storability of the liquids offer unique advantages despite their handling complexities. Now, what about when the missile hits? The real impact comes from explosives, compounds like RDX or HMX that rapidly decompose and generate intense heat and gas. To enhance the explosion, aluminium powder is added after the main blast. It reacts with atmospheric oxygen in a secondary afterburning reaction, releasing even more heat, as shown in the reaction. The secondary reaction significantly boosts the warhead's destructive potential, particularly against hardened targets. And it's not just about the explosion. Fragmentation materials like steel or tungsten are carefully designed to break apart into deadly sharpener. These fragments are what actually damage or destroy the incoming target. Next up, how do these systems find their targets? Missiles are infrared seekers to detect the heat of aircraft or missile. These sensors often contain mercury cadmium telluride, which is cooled using liquid nitrogen to improve sensitivity. Alternatively, compact systems use vanadium oxide for simpler uncooled detectors. Radar components, meanwhile, depend on advanced semiconductors like gallium nitride and gallium arsenide. These materials allow radars to operate at high power and frequency, key for tracking fast moving threats. To avoid being detected, many systems are coated in radar absorbing materials like carbon nanotubes or iron based paints, which absorb radar waves instead of bouncing them back. A missile must survive crushing speed and heat. That's where missiles material science step in. Carbon fiber composites give missiles a lightweight yet strong structure. For parts exposed to extreme heat, titanium alloys are used due to their high strength and heat resistance. To protect against aerodynamic heating, missiles are coated with ablative materials that char and erode, absorbing the heat so the internal structure stays cool. And in the corrosive environments, we now use cerium based coatings instead of toxic chromium ones, offering safety and durability. Missiles also need reliable power the moment they launch. That's where thermal batteries come in. They stay inactive until launch when a small pyrotechnic charge melts the solid electrolyte, instantly activating the battery and powering the missile. For longer term systems like radar units, lithium batteries are ideal. They provide steady, high energy over long durations. In the modern warfare, it's not just about offense, it's also about deception. The chemical compounds used in countermeasures are engineered to mimic or obscure the signature of protected assets. The enhanced survival capability is essential for ensuring the continued effectiveness of air defense systems in modern warfare. Through the careful manipulation of materials and chemical properties, countermeasure technologies are able to disrupt the ability of adversaries to accurately track and engage protected assets. This deception based approach provides an additional layer of defense, complementing the physical and technical capabilities of the air defense systems themselves. Infra- infrared flares are chemical devices that burn at extremely high temperatures, mimic the heat signature of an aircraft to trick incoming missiles. Obscurant smokes are engineered clouds that block vision and sensors, made from compounds carefully selected to scatter light or absorb infrared. From the selection of the right obscuring agent to the controlled release mechanisms, every aspect of obscurant smoke design is meticulously engineered to provide reliable and comprehensive concealment. Let's look at how these principles apply to real world systems. Russia's S-400 and S-500 rely on advanced solid propellants, aluminized with warheads, and JN radar systems. The S-500 can even target satellites and hypersonic threats, as it has a range of 600 km. S-400 with a range of 400 km range, and the Russia's premier air defense systems represent some of the most sophisticated technology in the field. S-400 offers 360-degree coverage. Most notably, it is designed to intercept hypersonic weapons and low orbit satellites, a capability few other systems possess. The US has a Patriot, THAAD, and NASAMS offering a layered defense strategy. Patriot with a range of 160 km with kinetic interceptors, THAAD with a range of 200 km with an altitude of 150 km. It targets short, intermediate range ballistic missiles using hit to kill technology. NASAMS it has a range of 50 km. For higher altitude threats, THAAD provides exo-atmospheric interception of ballistic missiles, while the NASAMS system developed with Norway offers flexible network-centric protection against air-breathing threats and at medium range. Israel's famous Iron Dome, David Sling, and Arrow 3 form a multi-layered shield using AI-guided interceptors and real-time tracking. Arrow 3 is an exo-atmospheric interceptor with 2400 km range against ICBMs. David Sling with a medium range of 300 km and Iron Dome has a short range of 70 km. Europe have three types of these systems with different ranges. SAMT Franco-Italian has offered a range of 120 km. Using Aster 30 missiles against ballistic missiles, cruise missiles, and aircraft. IRIS-T SLM with a 40 km engagement range, this system targets aircraft, drones, and cruise missiles. European Sky Shield is a new initiative to coordinate air defense across Europe, combining various national systems into an integrated network for collective security against emerging aerial threats. The Russian invasion of Ukraine has prompted a fundamental reassessment of European air defense needs, leading to an increased investment and development of the European Sky Shield initiative to create a more integrated continental approach to aerial threat deterrence. The Asia Air Defense System includes HQ-9 from China, which has a 300-kilometer range, and cruise missiles exported to Pakistan, Uzbekistan, and Morocco. Akash NG from India is a next generation system with 70-kilometer range with solid fuel missiles range of 360-degree engagement capability. KN6 or Ponage 5 North Korea is an indigenous system with claimed capability similar to S-300, though operational status remains uncertain. KSM Pegasus South Korea mobile system, short range system that integrates with future LSM for layered defense against North Korea. Asian powers are rapidly developing sophisticated air defense capabilities to address regional security challenges. China's HQ-9 system represents their most advanced export offering with a range of 300 km in its latest variants. The next generation of air defense is even more exciting. Laser weapons like Israel's Iron Beam can destroy drones at the cost of a cup of tea using high powered fiber optic lasers. Programs like Glide Phase Interceptors are being developed to develop hypersonic weapons mid flight. Artificial intelligence is being used to fuse radar, infrared, and command data into one smart defense network. All of this still depends on materials that can survive the heat, react fast, and deliver massive energy in teeny spaces. The multi-domain integration, there it includes space domain integration, cyber defense integration, electronic warfare resilience, and network-centric architecture. Cyber protection has become equally important as physical defense, with air defense networks increasingly targeted by state-sponsored hackers attempting to compromise systems before kinetic attacks. This has driven developments of distributed redundant architectures that can maintain effectiveness even when portions of the network are degraded or destroyed. Beyond this, we can't ignore the downsides. Traditional fuels and oxidizers like hydrazine and ammonium perchlorate are highly toxic. That's why safer alternatives are being developed. Insensitive mutations, such as those using FOX7, are designed not to explode accidentally. A critical safety initiative in modern defense is the development of insensitive munitions. This involves replacing highly sensitive explosives like RDX and X with less shock sensitive alternatives. Insensitive munitions are designed to withstand accidental initiation from impact fires or sympathetic detonations. Key chemical innovations for future defense include energetic nanomaterials, which offer significantly high energy density and faster burn rates compared to their micro-sized counterparts, leading to increased thrust and extended range for future missile systems. The green propellants, to address the environmental and safety concerns, there is a strong push towards green propellants. These new formulations aim to replace toxic traditional propellants like hydrazine with more environmentally benign alternatives such as ammonium dinitramide based fuels. These propellants offer comparable performance with reduced toxicity and safer handling, aligning with modern sustainability goals. The development of advanced composites materials, including ceramics, matrix composites, is vital for overcoming the extreme thermal and structural challenges of hypersonic flight. CMCs retain strength at much higher temperature than the conventional superalloys, making them ideal for hypersonic flights, missile skins, and engine components. This allows for sustained high-speed operations and increased maneuverability at extreme velocities. So, what we learned? Chemistry is not just behind the scenes, it is the scene. It powers propulsion, drives explosives, enables sensors, and protects systems through advanced materials and countermeasures. As technologies evolve from nanomaterials to AI guided lasers, the chemistry behind air defense will remain the foundation of global security. Thank you for your attention. I hope this presentation gave you a deeper understanding of how multidisciplines come together to protect our skies and safeguarding us. Thank you. Allah Hafiz.